right, that's the bell. That's the bell. When you guys come in here, be standard. You come in here, you do what? Notes out and open Chromebook. Every day. If I don't need that, it's not that big a deal if I say, oh, you can put that away. You'll probably be like, oh, I just got it out. Like, no, it's not a big deal. Now, scientific method. We got through the reading, yes? We went over, we didn't watch the movie though, or did we? Did we not? Okay. We're not going to. I've got a different video to show you. So, scientific method, we make observations, we think about the problem and whatnot. This is one that is such a famous experiment, they wanted to do it on the moon. So I'm going to kind of demonstrate. Let's do these. Mount this, and a hammer and my hairbrush. You don't like my hairbrush? No, it's pink. Yeah, why wouldn't my hairbrush be pink? It feels really nice. I really like brushing my hair. Guys, this was a gag gift from a student last year. They got I think it was for Christmas. They had a little bag and everything, and I opened it up. I just started laughing because I don't usually, believe it or not, I don't usually use brushes. Believe it or not. But I tell you, when I do, I like it to be pink. And it does feel nice on the scalp. It does feel nice. Which one, guys, if I hold these up at a certain height and drop them at the same time, which one's going to hit the ground first? The hammer, why? Because it's heavier. They probably both move about the same amount of air. This is a little bit smaller, so this would probably run into more air, right? So you think this one would hit the ground first? Okay. How about this? If I have a piece of paper, a little piece of paper, and that hairbrush, okay, which one's heavier? The hairbrush. Which one's going to hit first? The hairbrush. What if this one had the same, like, less drag? Like if I crumpled it up, which one would hit the ground first? The hairbrush. Why? So you are really doubling down on this. If it's heavier, it will hit first. It won't? Raise your hand if you think it doesn't matter. Okay. So it doesn't matter. The weight doesn't matter. Does the air resistance matter? Okay. So yeah, listen carefully. I mean, the paper was still up here, and oh, good. I was worried. I thought I broke it. So air resistance. So that's the thing. Other than air resistance, we say that if the weight is more, it'll hit the ground first. But I have some holdouts. Do you agree with that? Okay. Check this out.
Well, in my left hand, I have a feather. In my right hand, a hammer. I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Mr. Galileo was correct in his findings.
How about that? So apparently nobody had ever heard of Galileo doing that experiment. What was the stories with the Leaning Tower of Pisa, wasn't it? That he went up there with a couple objects and he dropped them and they hit at the same time. Now, if that's true, then certainly one of them couldn't have been much more drag on it from the air. Okay, so just think about this for a second. We had a theory way back. Aristotle said that the heavier object would hit first, and that just made sense to him. He was wrong, but he was so smart that people just accepted it. Well, that guy's a genius. If he says the heavy object is going to hit first because it's heavier, then he must be right. How many of you have ever taken someone's word for something because you thought they were smarter than you? Okay. That can be a mistake sometimes. They might be smarter than you most of the time, or maybe you just think they are, right? And you might end up getting the right answer and they might be wrong. It can happen, okay? So be careful with that. Galileo, it took, I don't know how many hundreds of years, or probably close to 1,000 years before Galileo came along, and he was really, really smart too. And he applied some math, and he actually did some experimentation and proved Aristotle wrong. Okay? And then we have astronaut David Scott in Apollo 15 doing the experiment with a feather and a hammer. And did you guys see it? From where we were sitting, were you able to see it? They fell exactly the same rate. So here's how that works, guys. We're going to do the math later this year with Newton's universal law of gravity, okay? All objects experience the same acceleration due to gravity near Earth's surface. So anywhere you go on the planet, believe it or not, there is slight variation based on the density of the Earth under your feet, but 9.8 meters per second squared is the approximate, depending on what your source is, 9.81, whatever, meters per second squared. Some textbooks will round to make the math easier. They'll say it's 10 meters per second squared. But it doesn't matter if it's a feather or a hammer, they both experience the same acceleration due to gravity. Does that make sense? So on the moon, gravity is only about a fifth as strong as it is on Earth. So the moon's gravity, so if I go up to the moon, I'd weigh a fifth of what I weigh here. That's a weight loss regimen right there, I tell you what. But I still have the same mass, unfortunately. No lipo going on the moon, I don't think. So the difference is the mass. It really is. But think about it this way. Let's see if I can get this right. The gravitational force is not the same as acceleration due to gravity. All right, if you are not done, finish it later. Finish it later for like homework or whatever, okay? All right, here we go, scientific measurement. We have here a cockpit of the Space Shuttle Atlantis. Space Shuttle Atlantis, if you didn't hear, landed last week after a long mission. Anybody gonna call me out? No, it didn't. Why not? Anybody know? Go ahead and Google machine it. Ask your Google machine, say, when was the last space shuttle flight? Yeah, don't guess. Look it up.
July 8th, 2011.
July 8th, 2011. So isn't that the year you guys were born? Yeah. All right. Shh. Most of you were born in 2011. Raise your hand if you were born in 2011. Okay, most of you. Okay, cool. So the space shuttles haven't flown since then. Fun fact. Does anyone know how the U.S. government got astronauts into space immediately following the retirement of the space shuttle program? You're asking me how. I'm asking you if anybody knows. Nobody knows? We asked somebody else to take our astronauts up. Who do you think we asked?
China.
We asked Russia. Good. A couple of you knew. Some other guesses earlier today was SpaceX. They weren't ready yet. They were still in trials on their rockets. They hadn't been certified to take live people because, crashes still happen, right? Now, SpaceX is doing quite well. They're regularly taking cargo and people up and back. But in 2011, the U.S. government literally had no plan to continue space missions other than to be like, hey, Vlad, Mr. Putin, right? President Putin. I forget, was he president then? He was still in the government. Now he's back president again. Hey, Russia, because we're so friendly with them, right? Now, we were friendlier in 2011 than we are today, okay? But can we bum a ride? It's almost like NASA's sticking their thumb out on the highway, right? Hey, are you going our way? And go ahead and Google search. Don't blurt it out if you find it first. How much per seat did Russia charge the U.S. to take our astronauts to the International Space Station? If you open your Chromebook, it works better.
Oh, I know it.
$70.7 million per seat. Now, is that one way or round trip? One way. It doesn't say. Okay, I don't know. Either way, that's a lot of money. Okay, so we were paying the Russians for rides into space. So now, eventually, SpaceX, because the push was to privatize. NASA wanted to have private companies like SpaceX do that work for them because the idea was that they would be able to do it cheaper than NASA could do for themselves. That's true, but we weren't ready yet. So there were some folks that thought it was foolish to retire the space shuttle program before we were ready. On the flip side, the space shuttles were like brand new state of the art, right? Google search. When were the first space shuttle missions? And how old was Atlantis when it last flew? So somebody find for me when they first flew, the shuttles in general, and someone else find for me how old Atlantis was when it last flew in 2011. Give me that first piece of information. 1981. So 81 to 2011 is how many years? 81 to 2011. 30. 30 years. The design was 30 years old on the spacecraft. So the government decided it's time to hang it up. And, I mean, they had the Challenger accident. What year did the Challenger accident happen? You guys heard of that? Where it blew up, or it came apart in the atmosphere. I think it was re-entry, wasn't it? It came apart over Texas. It's like, okay, we really need to retire these. What? 86 was Challenger or Columbia? Challenger. When was Columbia? I was getting confused. When was Columbia? 2003. Okay. So 8 years later, they're like, we got to wrap this up. How old was Atlantis? I guess, when was Atlantis made? Space Shuttle Atlantis? I'm curious. 26 years old. Okay. 26-year-old spacecraft that's come in and out of the atmosphere. How many times? When was it? How many missions did it fly? There's another question. 33 missions. So more than one mission per year on average. That's a lot of heating up and cooling down, replacing tiles, a lot of stuff. Do you guys see what I'm doing right now? What did I just allow myself as your teacher to do? Google stuff. Another way to look at it is I followed one question with another question. I allowed the answer to one to stimulate the next question. Do you guys see that? It's called going down a rabbit hole. Thank you. I like that, guys, especially for you all in my advanced class, but all of my students, like, go down. It's okay to go down a rabbit hole every once in a while. That's how you learn things that aren't scripted. Does that make sense? That's not scripted in a lesson. I got triggered by the picture of Atlantis cockpit, and we went down the rabbit hole. That's a good thing. Okay? Don't always have time for it, but it's important to make time sometimes to go down a rabbit hole. All right. Be quiet, eraser with arms. Measurement. Somebody read for me. That very first paragraph. Read nice and loud into it. Unfortunately, yours didn't come out real well. I don't know if it wasn't picking up or what. Go ahead.
The one where it starts.
Measurements.
Okay. Measurements are a basic necessity in science. Scientists have designed thousands of different tools to help in the vital process of measuring. In this image of the controlled parcel of the space shuttle Atlantis, we see dozens of readouts from measuring systems.
Yeah. So there are measuring systems. Toss it. Get it all the way to me, for crying out loud. Okay. That was a rough landing. So we see all these measurements in these different gauges, some analog, some digital. Imagine you're in the driver's seat of a car, because that's where you're going to be like in a year, right? A year or two, you guys are going to be driving if you want to. How many different gauges can you think of that are showing you measurements? Speedometer? The gas gauge. Am I at half tank or what? What? The mileage, the odometer. How far has this car driven? Or trip odometers, right? Where you can reset it just to see how far I've gone on this tank of gas or how far I've gone on this oil change or whatever you want. We're going to Disneyland. We're going to see how far it is. I mean, use Google, for crying out loud. What? RPM, which is what? Revolutions per minute. Okay, so how fast that engine is spinning. Good. Also known as a tach, right? A tachometer. Anything else? There's a few more. How about oil pressure? How about water temperature? The coolant, right? How about what? Tire pressure. Yeah, these new cars for years now, they've had tire pressure monitoring systems. Some of them allow you to see for every single tire what pressure it's at. Yeah. Battery. What about the battery? How it's charging. So it's actually going to show, most cars, it shows you how much voltage the alternator is putting out. What else? Anything else that you can think of? Okay, that's good. What?
The AC.
What about the AC?
Right.
On your climate controls?
Yeah.
Can you set it to the exact temperature?
Yeah.
The older cars is usually just a dial where you go to blue for colder and red for hotter. But on the new ones, you can set it to the degree you want, and the system will try to get you there. Yeah, absolutely. How about temperature? Like air temperature, right? Yeah. The volume on your speakers? Sure. Your sound system? Yeah. Good. So there's a whole lot of information we have at our fingertips or right there in front of you on the dash. Measurement. All right, notes, folks. Be ready to take this down in your notes. We already know that the observations are an important part of the scientific method. Hypotheses are accepted or rejected based on how well they explain observations. Some observations, such as the plant turned brown, are qualitative. What does that mean? Qualitative means you don't have numbers assigned to it. It's not on a scale. You're describing in common language a quality observed in whatever you're looking at. So in this case, a plant turned brown. Okay, cool. How brown? Exactly. Well, it's really brown. Let me put it to you this way. Has anybody ever gone to a Lowe's or a Home Depot or a Menards or an Ace and you go to the paint department and you pick out the color you want for your wall off of the wall of colors? You grab it, you bring it to the paint guy or gal, whoever's working behind the counter, and they take it and they go over to the computer, and what do? They type in a code. Okay, there's a code. Nowadays, they probably have one of those QR things where you scan it, but the computer then pulls up the what for the paint color? The recipe. Were you going to say recipe? Okay, so it pulls up exactly how much of each of the pigments to add to your base. Now, all that's done mostly automatically, right? They pull up the recipe, they press go, right? They put the gallon in or the quart in or whatever it is, the right base, and they press start, and the computer automatically dispenses the right amounts. That information is quantitative. There's quantities associated with it. Exactly how much of the different colors do we need to make a brown or whatever color you're making, okay? A quantitative observation includes numbers. A quantitative observation is otherwise known as, AKA, a measurement. We take measurements. A measurement is obtained by comparing an object to some standard. Anybody hear about King John?
Yeah.
King John was confronted with a problem, and he came up with an easy fix. So the problem was people would measure things with an easily accessible item. Let's say they want to communicate how big their house is. They could step it off and say, my house is 15 feet across. And then somebody else would say, oh, man, well, my house is also 15 feet across. And then you actually went to the two different houses and be like, this one seems a little bit bigger. That's because they're not using the same what? Not the same feet. They both used feet to measure, but they have different feet. So King John said, guys, this has got to stop. This is crazy. We're using my foot because he's the king, right? So they standardized. Somebody took a measurement of his foot and they would like share that information. Okay, this from now on is a foot, guys. If you're going to communicate, you have to use this standard. Now, fortunately for me, my foot is a foot. Your foot's not a foot. I'm sorry. Your foot's probably like, what, 3/4 of a foot tops. I don't know. I'm not going to measure it. Okay? But my foot's a foot. Is your foot a foot? You don't know. Maybe you should check it. Because if it is a foot like mine, I can actually get really close. If I'm wearing shoes, you know. But if you wear a size 12 tennis shoe, it's probably about a foot. Guess what? How many inches are in a foot?
Whoa.
Do we see something there? Okay. Now, not all sizes are numbered according to inches or whatever, but mine, it works out. All right. Any observation is useful to a scientist, guys. But if they're quantitative observations, they're probably more useful because they're more replicatable, right? If I write a science report or something and I'm using quantitative data, someone on the other side of the planet, without talking to me about details, will be able to replicate the experiment that I describe. Does that make sense? Even if the measurement is an estimate, scientists usually make quantitative measurements in every experiment. So even if they're not getting a ruler out, they'll say, well, it's about 20 feet. We have a general idea what's going on. Consider the following a pair of observations. So you have a volume of gas. So you have a volume of gas. Volume, right? Volume. Okay, three-dimensional volume. If we decrease the volume of a gas, the pressure increases. Does that make sense? Because you're compressing it. If you're making the volume smaller, but there's still the same amount of gas in it, you're increasing the pressure. Is that valid? Is it true? Does it make sense? Sure, all those things are true, but is it quantitative? Are there numbers involved? No, it's just saying the gas is decreased. Well, how much? I don't know. Then the pressure increases. By how much? I don't know. The second observation assigns numbers to it. It makes the observation quantitative. It says, hey, if you have 2 liters of volume and you reduce it by half, so now only have 1 liter of volume, the pressure is going to go for whatever this gas is. It's going to go from 3 atmospheres to 6. So if you reduce the volume by half, the pressure doubles. That's much more useful. All right, before we we'll do one more paragraph. Who wants to read this very next paragraph? Who wants to read it?
Do I start at the standard?
Since accurate measurement.
Since accurate measurement is a vital tool for doing science, a consistent set of units for measurement is necessary. Physicists throughout the world use the International System of Units, also called the SI system. The SI system is basically the metric system, which is convenient because units of different size are related by powers of 10. The system has physical standards for length, mass, and time. These are called fundamental units because they have an actual physical standard.
Awesome. 3 there. Fundamental units. Length, mass, time. I don't know why I'm talking into this. I've got one right here. If I'm about ready to go home, or if my wife's about to go home, it's standard operating procedure in our family to text or call the other person and ask what? Do we need anything? What do we need? And usually it's, oh, we don't need anything. We're going to go shopping tomorrow, or we just went shopping, or whatever it is. But oftentimes, what's the first thing you check? You open the fridge and you check for what? The milk. The milk. Who said milk? Okay. So food or whatever, need butter. The milk seems like it's a common one. Okay. How much milk do we have left? So if I ask her what we need, she's probably going to say, hey, we have a half a gallon of milk left. That tells, she doesn't need to say we need milk. She said it without saying it, right? If we've only got a half gallon of milk left, that's going to last one breakfast, right? If we're lucky, because we got a family of 6. Okay. So I'm going to say, okay, I'll pick up a gallon on the way home. And she might say, get 2, right? If we were in a metric system country, what would we be measuring our milk in? Liters. Liters. Good. How about this one? I live out in the country. I don't live like 2 blocks away or something. I live out in the country. I drove to work today. I went how many miles? But if I lived in a metric system country, we would say kilometers. Good. Good. How about this one? It took me how many blanks to walk up the flight of steps? I'm looking for time. Seconds, right? Because hopefully it doesn't take more than several seconds to walk up a flight of stairs. Might have to see the doctor if I'm out of breath halfway up, right? But if I was in a metric system country, we would use what? It's still seconds. Who said it's still seconds? Good, good, good. I was trying to trick you. How about this one? You check the weather and you see what the temperature is. In this country, we'd use Fahrenheit. But if we were in a metric system country, Celsius. All right, what's the freezing point of water? 32 in Celsius, or in Fahrenheit. 0 Celsius. All right, good, good. How about boiling in Celsius? 100. Boiling in Fahrenheit? 212. So people are always trying to decide which one's better. They both have their ups and downs, okay? Let's go this way. We run out of time, aren't we? How many degrees or increments are between freezing and boiling for the metric system, for Celsius? 100. What about for Fahrenheit? Between 32 and what is it? Yeah, 180. Between 32 and 212 is 180 degrees. So which one has a more precise, what's the word? Not more accurate. Yeah, more precise. The degrees are smaller. There's more increments between them. Fahrenheit. So you can make an argument there. But then you could say, well, it's easier to remember. I don't know. I can remember either way. All right, we'll keep going. Probably finish this lesson tomorrow. Have a good day.